Hello everybody, I hope you're all doing well. Root Beer here, as always, looking at more of our 2018 Cayley paper. We're up to question number 23, so if you haven't taken a look at that, feel free to pause the video and get a copy for yourself and try question 23 before continuing on. I'll assume you've done that if that's something you want to do, and let's take a look at 23 right now. So, question 23, a container in the shape of a rectangular prism stands on one of its triangular faces, so the picture I just drew is bogus. Something like this would be better. Okay. Three spheres of radius 1 are placed inside the container, each touching the triangular bottom. So, 3 spheres in there. Each sphere touches 2 of the rectangular faces, so they're sort of wedged into the corners almost. And each sphere also touches the other 2 spheres. So there's a lot of points of tangency, a lot of connection. That's a good thing to know. A 4th sphere of radius 1 is placed on top of the 3 spheres. And it's touching each of the 3 spheres and the top of the prism. So we actually draw our ceiling a little lower there. The volume of the prism is closest to, and then we've got a bunch of answers rounded to the nearest 1/4. Okay, so I'm starting to think, well, I should probably grab my calculator. And indeed, I do always have my calculator handy. We'll see if we can avoid it, but I'm thinking it's question 23 on a Cayley. We'll probably actually have to bust out the calculator. I could see values of pi maybe coming into place. All right, it's a 3D geometry picture, or a 3D geometry question, and I make no secret that I'm not the best at these, but I would like to think I've learned a trick or two over the years, because, well, if you find you're particularly bad at things like inequalities or something like that, it's a very good idea to sort of practice inequality questions so you're not so bad at them, so you don't fear them as much. So I'm going to draw a little 3D picture. So orange here, orange here, orange here. But you'll notice, and this is something I've noticed, is that 3D pictures are not the easiest thing to work with. It's very hard to tell what's going on unless you actually have some solid 3D props that you can play with. This is not the best thing for you. Although, sometimes props are allowed on contests. It usually depends on the instructions of the contest. And you can read the instructions for the Waterloo contest at the very start of each contest. And it also sometimes depends on the proctors that you're with. Some people think having visual aids is somehow cheating or something like that. But, for a question like this, having just 4 generic wooden blocks from a craft, not even wooden blocks, but wooden spheres from a craft store, or styrofoam spheres from a craft store, would work wonders. Okay? And even if you couldn't actually bring those into writing the contest this year, being able to sit there at home and play with them and be able to say, okay, here's the question, here's a real model, now how can I sort of commit this visualization and this information to memory, that's a useful thing as well. I found that a 3D picture is okay, but you can't really tell a whole lot from it. Usually what you have to do is break it down into 2-dimensional geometry by looking at it from the top down or from the sides or a couple sides and get different perspectives, because we're a lot more familiar with 2-dimensional geometry. We know about circles and tangent lines and triangles and angles and things like that a lot better than we know about things like dihedral angles or steradians or things like formulas for spheres and tangent planes rather than tangent lines. So if we can translate this into a series of 2D pictures that reveal the story, that's a good idea. Okay? Now, what things should we actually be looking at? Well, I'm inclined to look at it from the top or bottom down. I think that's usually a very good approach, and then we'll probably have to look at it from a side or something. I'm thinking looking at it right on from one of the sides as opposed to head on one of the vertices, but we'll see. So looking straight down, I see my spheres, and each sphere touches the 2 sides. Now the sides are these whole lines of this triangle. The spheres are packed in here so that they touch each other. I'm gonna draw a good copy of the picture, and so that means circles first. So they're about the same radius. Anyway, we'll draw our triangle in after the fact. Okay, so you'll notice that each of these spheres is touching two of the sides. Here are our points of tangency. They're also touching each other. Okay, so this is our top or bottom down view. Okay, but it's a two-dimensional picture. And did they say it was it's just a triangular prism? They didn't say it's equilateral, but by symmetry we can sort of see that this is going to be an equilateral triangle. Okay, so I see points of tangency. Immediately I start thinking, well, I should connect up points of tangency to the centers of my... They would be spheres, but they're going to be circles because it's a two-dimensional picture. And so tangent lines, you get right angles. Okay. And then, well, you'll notice that all of these are the same radius. They're radius of 1. So right away inside here, we notice we have an equilateral triangle of length 2. Of side length 2 there. And we can learn other things from here. So we've got some right angle triangles we can play with. We've got some... These are going to end up being rectangles that we can play with. So this side here is 1 plus 1 is 2. Okay. If I were to zoom in just on a corner... I've got these tangent lines here coming from the center. Let's draw that a little better. So we both have a radius of 1 here. If we connect up here, we've got a nice little right angle. We're going to have 1. We've got right angles on the other sides. These guys are, in fact, going to be little rectangles. And if we've got an equilateral triangle in the middle, that's 60 degrees. So what's left over here? 120 degrees. 120 plus 90 plus 90 plus 60 will, in fact, make a nice little 360 all the way around the center here. So splitting this 120 in half, which we can do sort of by symmetry, we get 60s here, we get 30s here, and so what have we got? We have a 30, 60, 90 triangle, and I know the side opposite the 30 is length 1 because it's the radius, so this hypotenuse here is 2, and this length over here is going to be root 3 because 30, 60, 90 triangles have sides in the ratio of 1 to root 3 to 2. So on our big picture, this part here is a root 3, this part here is a root 3, and this is an equilateral triangle. We can see because the same pictures are reproduced everywhere. Okay, so now I know the sides of the base of my triangle. It's 2 plus 2 copies of root 3. So we've learned a little bit. And we could actually figure out the area of this triangle. We could figure out its perimeter, but I'm more focused on the area because what do they want? They want volume. And one might say at this point, or one might have said earlier, how do we find the volume of a prism? Well, really, for any prism with any shape bottom, you just figure out the area of the bottom, call that area A, and you multiply by the height. So we'd have to figure out two things, the area of the bottom triangle, which we can now do, and the height. And to figure out the height, well, we've got to do a little bit, oops, I went down. We have to do a little bit more work. We have to look at it from the side, so we can use this fourth sphere here to help us determine the height. Okay, so equilateral triangle side is 2 plus 2 root 3. We'll use that in a little bit, but I want to get my second picture out here. So we might say side view. So the sides of a prism, of our triangular prism, are going to look like rectangles. On the bottom we have our two spheres. Now this side here is going into a corner, so we have to be careful because our spheres don't actually meet the corners. We can see they fall short if we just look at it from the side. Yeah. So we've got that, but we don't actually need that. So here's our second sphere, and then we've got another one back here, and then we've got that fourth sphere up on top, and it's comfortably touching each of the others, and it also touches the height here. So I guess we can, I guess we can get rid of this top bit here and slightly redraw our picture. Okay, so how are we going to figure this out? Well, again, we sort of have some connections we can make. So these spheres are touching the base of our prism, and this sphere is also tangent to the top of the prism. So we get nice little right angles here. Okay, and then so it's not quite that they're sitting comfortably on top of each other. We sort of have to imagine, well, this point here and this point here, they're connected, and these spheres are all connected. They actually make a nice little tetrahedron. Okay, these spheres make a tetrahedron of radius 1 plus 1, which is 2. So the height that we want is, let's use purple, radius of 1, and then radii of 1 down here, and then the height of a tetrahedron of side length 2. Okay? How do I figure out the height of a tetrahedron if all I know is the side lengths? Okay. So 2, and then we pop up here. So the sides here are all 2. Okay. But the challenge is, well, how can I figure out the height here? So we want to go from up there to, and all of these are 1s here. So the red dot is sort of the center of our tetrahedron, and we have, oh no, I guess the sides aren't 2. No, silly me. It's the distances to the center are all 2. Right? Yes? Hold on. No, I think I was right the first time. The sides are 2. This is what I mean when I say I'm bad at 3D geometry. Let's redraw. So we'd have through the sphere connecting up to the, so we've got a top point and we've got the centers, and we connect centers up through the tangent points of the spheres. So yeah, the sides of my tetrahedron are going to be 2. Center, center, and center, and this is the center of that further back sphere, and there's our centers. Okay, so how do I figure out the height of a tetrahedron? Well, we sort of need to break it up into a few more two-dimensional pictures. So what I would do is I would drop an altitude from the top center to the plane, the bottom here, and this is going to be what connects, actually this. Let's use the light blue just to connect back and try and understand our previous picture. This blue triangle connecting the 3 bottom spheres' centers, it's all just going to be this triangle right here. And all it is that it's been raised in the air by a radius of 1. Okay, so that's the center of the base there. Now I can figure out the distance from that to one of the corners, and because it's an altitude, we make a nice little right angle, and this gives me a triangle, a right angle triangle. It's got my height that I want, h, so we get 1 plus 1 plus h is the height of the whole prism. So this h here, and all I need to do is figure out the distance from the center of an equilateral triangle to its side, and I know the side lengths are 2. Okay? So we just have a little bit of work to go to do with equilateral triangles. So let's investigate equilateral triangles a little bit, refresh some formulas that we might know but couldn't remember, or learn some new formulas if we didn't already know them. So if I have a side length of s, I need to figure out the area. So I would drop a right angle here. Equilateral triangles have 60 degrees in the corner, so it's another 30, 60, 90 triangle. The height here is going to be root 3s over 2, because the side opposite the 30 degrees are going to be s over 2's, because it's an equilateral triangle, therefore it's an isosceles triangle, therefore the altitude makes a right angle and splits the base in half. So there's the height, and so the area in terms of the side length is going to be 1/2 base of s times height root 3s over 2. This turns into root 3s squared over 4. So that's the area of our an equilateral triangle in terms of s. Now, for the center of the triangle to a corner, well, how can we figure that out? Well, the center is going to be placed right in the middle. It splits the 60 degrees into 30 degrees, making a bunch of really nice isosceles triangles. We know the side length, let's call it s. So s here is our side length. And the portion of the altitude, so the distance to the corner, let's call that c. I know that if I've got c there, and if I drop another right angle here, so c, it's going to be the same c in each case. But c plus this sort of mini height here, maybe call it d, c plus d is this root 3 over 2s that we already knew. But the nice relationship here is we've got d is on the just opposite the 30 degrees in another 30, 60, 90 triangle. So d 2 times d is going to be c. So really we've got 3d is root 3 over 2s. D is going to be root 3s over 6. And c, the length that we want, is just multiply d by 2. So root 3s over 3. Okay. So now putting this all together, we need the area of the base. And the base of our triangular prism has side length 2 plus 2 root 3. So the area is root 3 over 4, 2 plus 2 root 3 squared. The height is equal to 2 plus h, where h, you might remember from just a little while ago, h is part of a right angle triangle that has that c as the base and side length of 2. And what was c? Well, c we just figured out is root 3 side length over 3. So h squared plus 3 times 4 over 9 is equal to 2 squared, which is 4. Okay, so what have we got? Multiply everything by 9. 9h squared plus 12 is equal to 36. So 9h squared is 24. Divide by 3, so you get h squared is 8 over 3. So divided by 9, we get 8 over 3. And so h is going to be 2 root 2 over root 3. So now we can bring that in, and the height we want times the area we want, that'll get us our final answer. So volume is area times height. So that's root 3 over 4, 2 plus 2 root 3 squared, times, what did we just figure out? 2 root 2 over root 3. So some nice things. Those will cancel. Most of this will cancel, leaving a root 2 on the bottom. Now let's just square the top here. And I'm going to square it and expand it out. Of course, at this point, you could just grab your calculator. But we'll get 4 plus 4 root 3 plus 2 times root 3 is going to be 2 times root 3 times 2 times root 3 is going to be 12. This is all over root 2. Something doesn't seem quite right because these numbers don't seem big enough. But I'll just grab my calculator and plug it in anyway. So that's 16 plus 4 root 3 all over root 2. Of course, the root 2 can go away, so we'll get 8 root 2 plus 2 root 6. 8 times square root of 2 plus 2 times the square root of 6. Yeah, I'm getting 16.21, which is nowhere near the answers presented here. So, what am I doing wrong? Okay, so this first thing I've noticed I'm doing wrong is I'm using this h, not 2 plus h. Let's see if that changes things. So I was pretty confident in the area we got, but the height, yeah, so we missed the 2. So 2 over 2 root 2 over root 3. Let's cancel out the root 3 of it all. So that'll be 2 plus 2 root 3 squared over 4 times 2 root 3 plus 2 root 2. We can pull out a 4 on top, so 4 times 1 plus root 3 squared all over 4. Those will cancel out. Times 2 root 3 plus root 2. And so 1 squared is 1 plus 2 root 3 plus root 3 squared is 3. So that times root 3 plus root 2 times our 2. There we go. And so that's pulling out another 2. We can get 4. 2 plus root 3. Root 3 plus root 2. I don't really see the point in simplifying that anymore. You could have stopped a long time ago, but let's do square root of 3 plus square root of 2 times 2 plus the square root of 3 times 4, and that's looking much better, so I'm getting about 46.968. We want to... Oops, I wrote 698. Okay, so 46.96807. So we would round that up to 47.00. That's to the nearest quarter. And that is an answer of E. So there we go. We got our answer of E. Only a tiny little fumble I made in terms of the height. I used the wrong height just for a moment. But there we go. That finishes off question number 23. Up next will be question number 24. We are almost done our Cayley paper. And if you would like to, I encourage you to try the last 2 questions if you haven't already. Until the next videos, take care and have a wonderful day.